So far we talk about the cosmological perturbations in the various video. We started in the Newtonian approaches and we turn to the gravitational general relativity. And in the last time we discussed sort of about simplifications to sort of the GR versions with the superhorizon and the adiabatic condition. And today I will talk about the matter perturbations, and maybe next time I will turn to the radiation component. So the in the superhorizon and adiabatic condition, the matters and the radiation perturbations are simply determined by the metric perturbation capital pi. So the superhorizon limit, the K inverse is rather than the Hubble scale, and the adiabatic conditions impose that the radiation and the matter perturbations are directly connected with the simple coefficient. And we know that the radiation perturbation delta R can be written by the metric perturbation from the 0, components of the Einstein field equation, and this capital pi behaviors of the metric perturbation can be determined by the ij components of the Einstein field equation, and in the superhorizon mode the solution is given by just a constant. But when the universe transitions from the radiation to the matter dominance, this metric perturbations slightly changes, and by using the gauge invariant quantity, curvature perturbation currently R, this is a constant over the all the universe of the history. So when the universe transitions from the RD to the MD, there will be the 9 over the 10 factors for the metric perturbation. So now I will talk about some general evolutions for the matter perturbation, not only the superhorizon. So to determine this matter perturbation, we first know that how the matter perturbation or the gravitational potential capital pi is evolved over the cosmic history. This is a generalization of the number 4 in the review. So including the superhorizon and the subhorizon, we need to solve the ij components of the Einstein field equation. And there are also the two dominant errors. First, the simple one is the matter dominant one. The matter dominant error is the equation of the state W is just given by the 0. So the matter perturbation has two solutions. One is the constant mode and the other is the decay mode. And for the radiation dominance universe, the equation of states are just one of those. So the equations are just reduced to this form. And the solutions of this second sort of the difference equations is given by the Bessel functions. So this is some complicated form. And we can take the limits for the superhorizon and the subhorizon. Where here is the curly parts defined by the new variable, whereas the k is the correspond to the momentums and eta as the component time. So the small curly pi means that the k is smaller than the eta inverse, the component time. So this is given by the Hubble scale. So this corresponds to the subhorizon, and if the curly pi is the last, this corresponds to the subhorizon. And now we can know that for the superhorizon limit, the capital pi is given by just constant one, related with just curly r, the curvature perturbation. But for the superhorizon limit, this Bessel function expansions given by the oscillating behaviors with reducing amplitude. So that we can plot this radiation dominant during the radiation dominant eras, the behaviors of the metric perturbation. So here's a plot. So these moments, equilibriums, mean that the universe transitions from the R to the MD. And now here this is the matrix perturbations over the scale factors, the cosmic history. So the capital pi's are given by some initial value. This is determined by the some primordial fluctuation, which we will cover in the next time. And the this k equal to k equilibrium means that this k mode enters the sub-horizon when the a is equal to the a equilibrium, RD to the MD. So in this case, originally this K mode, K1 modes originally in the superhorizon, but it enters the subhorizon because the Hubble decreases, so the Hubble inverses are increases. So for the specific K mode, it originally outside of the horizon, so superhorizon limit, but it enters the subhorizon in the right-time universe. So this is K inverse. So for the small K inverse, which means that the large K, this enters the horizons enter the subhorizon more earlier. So here's the Hubble inverse K inverse, and in this case the K inverses are more small, so it entered the sub horizons more earlier. So now this movement is starting through the sub horizon during the RD. So it got the oscillating form, but the oscillating amplitude will be decreases. And in this case, the K mode entered the horizon at the transition from the RT to MD, so that we cannot see the oscillations motion. And also this mode entered the horizons after the equilibrium. So also there are no lighting behaviors. And during the MD, all the matrix perturbations are given by just a constant value. But for this one, there's only the 9 over the time factors changes for the sub-horizons oscillatings. I mean, there's this given by the solutions of superhorizon, and at some specific time it enters the subhorizon, so that there will be the none of the time factors about the superhorizon's limit. So now we know how the capital pi, the matrix perturbations, evolved through the cosmic history. So now we can determine how the matrix perturbations varies over the cosmic evolution. But for the case of the baryons, it is coupled to the photon before the recombinations of the cosmic history, but dark matters does not. So that this gives the different behaviors for the baryons and dark matters for each case. So for the sub-horizon case, we already know that the Newtonian's results, the matter perturbations follows the logarithm growth for the radiation dominant era, and for the matter dominant era, it grows linearly. This is consistent with the Newtonian approaches. This can be also shown by the conservation equations for the dynamics result M, and also the capital pi is determined by the Einstein field equation. The for the radiation dominance, whereas the capital pi contributes from the radiation component, so that it gets utilized solution. And then we can reproduce the Ramassagero equations in the Newtonian approaches. But for the superhorizons limit, just the delta m's are given by just a constant, because the capital pi is a constant for each era, while the radiations are rather dominant. So when the specific K moves enter the horizons, then it starts to close following the subhorizon. So there's a Hubble inverse. K enters to the specific K moves enter from the subhorizon to the subhorizon. So here's some different K mode. First of all, for example, in this case, the K is smaller than the k equilibrium. This means that the k inverse is larger than this one. This is a equilibrium. So it enters the horizon slightly. So it means that the starting of the growth, the lightest, it starts the growth here until some specific subhorizon, and it starts linearly growth. For example, in this case, this Hubble inverse, and this is I equilibrium, and this is K inverse. So it entered the subhorizons before the transitions. This means that during the RD, it got the subhorizons previous with the logarithms of the I. After the transitions, it follows linearly growth. So depending of the K mode, the entering moments are different, so the growth behaviors different for the RDs and MD, and also we should consider several superhorizons. So there are some several criteria. First of all, we can determine some specific K modes. This have the different moments for the entering the some horizons. So when some specific K modes enter the horizon starts, and this transit to the subhorizon to the subhorizon, and also we can classify this entering moments the before the equilibrium or the after the equilibrium, and depending on the growth behaviors are quite different. So we can classify that there are four types: superhorizon, subhorizon, RD, and MD. For the superhorizons, both the RD and MD just are constant, but the subhorizon RD is the logarithm A, and for the MD this is just linearly growth. And some specific moments the K mode enter the subhorizon, and the moments can live in the RD or stationary MD depending on the size of the K. So this is the story of the matter perturbation. But also there are also still remaining story. We can plot the matrix power spectrums in terms of the transfer function. The projections matter power spectrum are determined by the two component first of the initial conditions, which is given by the primordial curvature perturbation generated by the impulsion. We will cover the latest. This is the first one. The second one is some linear evolutions that we discussed in the slide. This includes the information of the how the matter perturbations are evolved. So this is the primordial perturbations, and this is the transfer function how the matter perturbations are evolved, and finally the matter spectrums in the presence are determined. So P curly RK is a primordial curvature perturbation, which is the nearly scalar invariant, and the capital T is the transfer functions, including the factor of the RT and MD. So to deal with the primordial curvature perturbation, this can be obtained by the curvature perturbations of the Fourier transformation from the position space to the momentum space, because there is some dimensional quantity, the curly R acts as the dimensionless. So the Fourier transform has a dimension of the k minus cube, and the power spectrums are determined by the 2-point correlation functions of this curly RK, and in the left hand side the dimension of the k to the minus 6, and the delta function has the dimension of the k to the minus 3. So this power spectrum P curly R has the dimension of the k to the minus 3. So we can define the dimensionless spectrum by multiplying the k cube for the P curly RK. So now we can get the primordial spectrums in the dimensionless quantity in terms of the capital delta. And already we discussed that this plot. So if the K mode is some large, then the K equilibrium it enters the horizons before the A equilibrium, but if the K is smaller than the K equilibrium, it enters the horizon after the A equilibrium. So, a lot we discussed. This determines the second component of the matter-power spectrum. So let's talk about the first case, this one. The mode enters horizon during the matter dominant after the transition. So the this moment can be evaluated when the K modes is the same to the Hubble horizon size, and during the MD Hubble that given by the this is just a Boltzmann equation. During the MD, loads are reduced to the right to the -3. So that this is just given by the AK minus 1/2. So now we can determine this mode AK. And during the matter perturbation, during the MD, the matter perturbation goes in the subhorizon linearly. So the delta goes linearly. So square root of the deltas goes the scale starting from the AK when the K modes are entered the horizon. So we know that this AK is given by the K minus 2 from this relation. So now we can get the delta scales that proportional to the K to the 4th. So this is the first case. Case is smaller than the K equilibrium. So when the K is smaller than the K equilibrium, delta is proportional to the K to the 4th. This means that the entering moment in the MD and this means that the transfer function is given by the K force for this case, and now we can evaluate the matter power spectrum. Because originally the primordial perturbation has the K minus cube, so the times of the K minus cube primordial one. Then the matter power spectrum has a linear behavior for the small k. Now we can watch the second case. K is rather than a K equilibrium. In this case, the K modes enter the horizons during the RD. So the AKs are determined by during the RD. Same equation, but now the Hubble satisfied this relation from the Boltzmann equation. There's another radiations, and by inserting that, the K is proportional to the AK to the -1. And during the radiations dominance era, matter perturbation grows in the subhorizons, the follows the logarithm behavior. So the delta scales the follows the logarithm of scale. But during the MD, it also got the linear growth, but there is no scale dependence. This means that there are no K dependence here. And by inserting the relation between the K and AK, then the delta scales are proportional to the logarithm scale. So the transfer function for this case, K rather than K equilibrium, is given by the logarithm K scale. So by multiplying the primordial perturbation k minus cubes, then the power spectrums get the k to the minus 3 times the logarithm k square. But the logarithm, if we ignore this logarithm, then for the large k or the small scale, the matter power spectrums decrease to the k to the minus cube. So the depending on the k equilibrium, the matter power spectrum of the different structures. This can be determined by the different transfer functions, whether the transition moment from the superhorizon to the subhorizons in the RD or MD. So, oh yeah, that's a very um, long story. So the above discussions only applies for the cold dark matters, not for the baryon. The cold dark matters are negligible projects, so that they can only grow still in the logarithm during the RD. This growth is inefficient because the radiation compounds are dominant, but this logarithm growth produced a small scale behavior k to the minus 3. But in contrast, for the baryon, this tightly coupled to the proton before recombinations and get the acoustic oscillation. So I will cover this proton baryon fluid in the next time. And let's talk about the dark matters more. So for the large scale, small k, all the matter power spectrums are identical for the mode. But for the small scale, this right-hand side of the plot, depending on the dark matters, the matter power spectrums are quite different. So the core dark matters still remains the on surplus power spectrum for the small scale, but dark matters like the warm dark matter or void dark matter or interacting dark matter model has a suppression due to the pre-streaming projects like quantum impacts for the small scale structures. But this is some other scopes in the standard cosmology textbook. So today we talk about the very long stories about the matter's perturbation. The matter power spectrums can be determined by the primordial perturbations and the following evolution during the RD and the MD era. The superhorizon modes can be determined by the matter perturbation and nearly constant, but for the subhorizon modes, this get the scale dependence growth. Depending on the RD and MD, for the RD it gets the logarithm dependence, but for the MD it gets some linear dependence. And when the modes enter the this subhorizon modes, then the matter perturbation starts growth, but this entering moments might be different whether it's RD and MD, and this determines some characteristic turnovers at the K equilibriums across the small scales and the large scale. And the detailed small scale structures encode some microscopic properties of the dark matter. So today we talk about the matter perturbations only, but in the next time I will turn to the radiation components continually, and this will be connected to the cosmic microwave background CMB and some tight binding between the baryon and the photon fluid.